Ah, Gary, it seems like you're about where the top physicists were about 100 years ago, and like I said, happened to be reading this biography of Einstein. So it's very interesting because these are the questions whether there were particles. So let's clarify a couple things. First of all, Einstein really is an ally of yours in the sense that he had some idea that there should be a continuum, this discrete, the idea of particles doesn't really fit well with classical physics, Newtonian physics. Sure, there's ancient atomism, but in terms of classical physics, the idea was this continuum, and there's various things like gravitational forces acting instantly. And there's got to be a continuum because in a continuum, if it's going down, you could say, oh, it's going down. If it goes back up, you can, oh, well, there was a reason it went back up. But with the spontaneous emission of photons and stuff, that's difficult. Now, in the wave particle duality, I mean, basically, it's true. I don't. Both of those can't be true. You need some higher abstraction that encapsulates both of them, and it's clear that you can do that with a wave-like abstraction, but not with a particle abstraction. Now, the important issue is there's a couple issues. Okay, first of all, I want you to think again about, or everybody or whomever's listening, you drop a pebble in the water. As the pebble gets smaller and smaller, the ripple it creates gets smaller and smaller. And in electromagnetism, let's say you have, well, forget the antenna for now and just think about it this way. If you have two little antennas and you create a difference of voltage so that a little spark goes, that little spark will cause a burst of electromagnetic energy, a ripple of it that shoots out at light speed. All right. If you make that smaller and smaller, that spark, and indeed the spark would be between one wire and you wouldn't see a spark, it would just be a little tiny movement of an electron wiggling something. If you move that lower and lower, this ripple gets smaller and smaller until finally it breaks down and you see that, yeah, it seems to be particles shaken free. Okay, that's interesting. And you can lower it down to where you just get one photon, just one, shaken free. And it acts like a particle. It has a spatial location. Okay, and you can demonstrate this with something as simple as photographic paper. Very clever to explain how it works. Thank you, Einstein. But once you have one, it's like, yeah, it hits and it makes a dot. Looks like a particle. It's behaving like a particle in that situation. Okay. But the weird thing is you've lowered it down and you get a particle off. So this goes with the, hey, we're just shaking particles off of some system. And this is what Planck, who discovered the quanta of energy, believed. He said it's not like there's a photon, a single particle. No. I mean, obviously light is this wave, this propagating wavefront. So it's not like there's a single particle. It's just that this is a feature of, like you say, a feature of the slits. It's a feature of the body that's radiating and those interactions. Okay, but Einstein showed that no. And subsequent, we showed no, there's photons. They can be isolated as single particles. So that's fine, but then the question becomes: are they really what are they like as particles? And are they really particle-like? Do they still have wave-like behavior? And why do waves come from them? It's true you can get wave-like behavior from systems of particles, right? But there's certain things you can look at very closely. So, for example, a particle, bullet. If I have a gun with a muzzle speed of, I don't know, 200 miles per hour, probably not that much for a gun. I don't know what guns are supposed to have. And I fire it from a train coming at you at 50 miles an hour, then the bullet is coming at you at 250 miles an hour. That's a particle, the addition of those velocities. But if I fire a loudspeaker, there'll be a Doppler effect, but the waves will still come at you at the speed of sound through air, 700 miles or so an hour. So that's one thing. They noticed that when you were putting voltages and creating light from cathodes and these kind of, ray tubes and these kinds of things, that the amount of energy, there'd be more energy coming at you, but it wouldn't be coming faster. Now, if you put more energy into a system and knock off the loose particles, the particles themselves come off at a higher speed. But with light, when you put energy into the system and get light out of it, they don't come at a higher speed. They simply come at different frequencies. Okay, so that's more wave-like than particle-like. But more important is that two-slit experiment, because particles and waves act in two different ways when presented with a screen. For obvious reasons, right? A wave is coming at you and gets masked by the screen, whereas a particle either hits the screen or a hole. It doesn't care if there's one hole or two or five. It just cares, does it go through one or not? Okay. So the weird thing about when you create this tiniest spark that just puts one photon off is that it turns out it looks like a particle if you look at it one way, but looked at another way, it looks like a very thin ripple. The one photon is one ripple, and it looks as though it's going out in all directions. That's how come it can hit both slits, because it's going off in more than one direction. That's what makes the wave property inherently, important and fundamental. Okay, it goes off, it shows that it goes off in more than one direction because it shows the properties of having a wavefront that hit both slits, interacted with each other, and yet on the other side of the photographic paper, you get the particulate behavior, one at a time. So there comes to be no way to explain how the photon works without both behaviors. But in the end, yes, if someone expects that these need to be unified, as Einstein and I and you and everybody would think that these generally would have to be unified now, they're going to be explained in terms of some sort of wave function. The particle is going to be like a standing wave, where you have a vibration that seems to stay in place. Really, things are vibrating so that at this place, the behavior is somewhat regular, and there's a localized phenomena that you can analyze in itself as a system. But really, it's a standing wave in this quantum field. Okay. Now, the main thing against the idea that when you put energy into the antenna and you get photons out of it, that this is, the main idea that this somehow is shaking off loose particles, that is contradicted by the fact that those particles leave with very regular characteristics. You know what I mean? If you have a rod that glow, a neon tube, if you put more energy, the neon photons don't come at you any faster. Each one doesn't have any more energy. You just get more of them. Okay. And this is a fundamental thing when you're looking very closely. And you want to remember that Einstein, yes, an ally on your side of things, that they should be continuous and predictable in the end, fundamentally an enemy of quantized particles in that sense. Still, because of his empirical, straightforward rationality, happened to be the one that demonstrated, more or less, that these that molecules, particles, were not just mathematical conveniences, that there was some material reality to them in isolation, say in a vacuum or alone. Okay, so he demonstrated that, and then he spent a lot of the last half of his career, at least, basically trying to unsuccessfully overturn that. He's been through a few ideas. Okay, so in your draft science, you might want to keep in mind that somebody that astute, had went out into the wilderness, God only knows where, and covered some sort. I'm not saying don't cover that territory. Maybe he missed something from his own predilections, but it's not like it has been unexplored, and Einstein isn't the only brilliant person to explore it. Now, continuity can be reclaimed. The problem with it is that for continuity to be reclaimed, we have to explain why we see a point, a particle type phenomena, when there's a wave, and that requires higher dimensionality, which means in some sense that there's a higher dimensional space, extra dimensions we don't see in. So the ripple is coming out. If you could see in enough dimensions, you'd see the ripple, but you can't. So you see a cross section of the ripple. What's the cross section of a ripple? A little dot. What's a cross section of a circle? Of a circle is two little dots. Of a sphere, is a circle. We're seeing this lower dimensional thing. That's how continuity can be reclaimed. The problem with that is that that's very counterintuitive as well, and brings us into all this multiverse stuff you don't like. But the problem is that where we have to go, we have some choices, but all of the steps so far before us are difficult to take. That there's other dimensions with other versions of things we're familiar with. That seems a little bit odd. But the fact is, this wave-particle duality is really undeniable. When you put a little tiny 1 quanta worth of energy into this antenna that's going to broadcast a photon, and just one photon comes out, it's acting like a particle. You can see, hey, it went in north. It's a particle, went in a particular direction, has a path. and yet it's also still acting like a ripple. And the way you can tell about the ripples is to